we talked about the concept of information and how it is to be measured or defined, both from intuitive as well as engineering point of view. And we also looked into the definition of what we call entropy of a source in terms of both the information measure as well as entropy of the source are attributes of the source itself, and they are really defined by the message probabilities, the source symbol probabilities associated with the source.
It's not clear how for the continuous distributions define it.
As I said, for the time being, for convenience, I am taking discrete sources. If we have time, we will look into continuous sources. I plan to do that, right? But for the time being, we are looking into discrete sources because it's easier to formulate these concepts in terms of discrete sources. The basic definitions will remain the same. They will not change from when you go from discrete to continuous. The concepts will be the same, but some of the details will obviously be different. In any case, we also looked into the concept of entropy, and by taking an example of equiprobable sources, that is a source in which the message probabilities are all equal, we could appreciate the fact that it is possible to represent this source by an average number of bits which is given by the entropy of the source, average number of bits per symbol. For representing a symbol on an average, in fact for equiprobable, all symbols will require the same number of bits, right? For equiprobable sources, all symbols will require the same number of bits, and that will be equal to the entropy of the source. And another result we discussed was that for entropy of a source to be maximum, all the message probabilities should be equal. So these are some of the results we discussed last time. Now we will continue on that discussion today and try to show, to start with, that even for a general source in which the various message symbols may not be equiprobable, it is possible to encode it in such a way that the average length of the code required to represent every symbol of the code, every symbol of the source, is still equal to the entropy of the source. That is, somehow entropy is largely to be now interpreted as a measure of what is the minimum number of bits required, or on an average how many bits are required to represent the source digitally using binary digits. Okay, so to discuss that, as I said, I think we had already started on this aspect. Let us consider a source M with message symbols given by n message symbols m sub 1 to m sub n. And let us say this is associated with a probability vector p sub 1 to p sub n. That is, message symbol m1 is associated with the probability p1, m2 with p2, and m sub n with p sub n. What I want to demonstrate that even for a source distribution of this kind, it is possible to think of entropy as the average number of binary digits required to represent each symbol of this source. The average value, of course. Actual value will be different from symbol to symbol, right? And I will try to demonstrate this through construction, that is by showing a procedure, an encoding procedure, wherein this will be possible. Okay, so let's look at that. The construction procedure that we will adopt is as follows. As I said, we are considering a memoryless source. This is another assumption that we are making for the time being. All right. What is a memoryless source? That is, from symbol to symbol, the emissions are independent, uncorrelated. So we will consider a message sequence coming out of this source. Right? Let's say the length of this sequence, message sequence, is n. Okay. So in the first entry of the sequence will be one of these symbols, the next one will also be one of these symbols, but picked up randomly and independently from the previous one, and so on and so forth. So we'll essentially have, let's say, some arbitrary message sequence. Maybe this may be a typical example. Right, going up to some value, whatever it may be, m sub k, where k goes from 1 to n, but the total length of the sequence we are considering is n. Arbitrary, n is arbitrarily large to start with. Okay, picked up randomly from this message, because let's say these are the consecutive. Let's assume that these are the consecutive emissions from this source in every succeeding interval of time, whatever the unit of time may be. Fine. Now let's just analyze the structure of this n symbol message sequence that we have got to start with. Right. Let us try to analyze it for how many of these symbols are going to be m sub 1, how many of these are going to be m sub 2, and so on and so forth. What can we say about that? Provided that n is sufficiently large, right, that is, if n tends to infinity, it's quite easy to argue from the basic understanding of the probability definition of probability that you might have as essentially relative frequency of occurrence of a particular event. Right, that's how you understand probability, relative frequency of occurrence of a event in relation to the total number of trials. Right. So if our total number of trials is n, that is the total number of symbols I am considering is n, and n is very large, n tending to infinity, what can we say how many times the symbol m1 will appear in this message sequence? p1 times. So m1 will appear n times p1 times. Similarly, m2 will appear n times p2 times, and so on. M sub n will appear n times pn times. Okay, and this fact is independent of what particular message sequence is actually being considered. Right, this message sequence may be different from one instance to another instance. Right, in this case I have got this particular sequence. In another case I might start with m1, go to m3, m5, and so on and so forth. Right, no matter what particular message sequence of length n is being considered, the structure of this sequence will be such that it will have so many times, so many occurrences of m1 and m1 times, so many occurrences of m2, and so many occurrences of m sub n. All right, this is independent of the actual sequence that is being emitted by the source in a particular situation. So if I call this typical sequence S sub n, right, so this is just a notation for the typical sequence that we are just considering, then we can say that the probability of this typical sequence S sub n, what is this going to be equal to? The probability of occurrence of this specific typical sequence that we are considering. Right? Let's say what is the probability that this specific sequence would have occurred. Will order matter? Order will not really matter. What is going to really matter is
number of message sequences possible.
Yeah, best thing is to look at the total number of sequences possible, and then 1 by n of that is one way of looking at it. Alternatively, we could just appreciate that each of these symbols is independently being emitted. All right. So the specific sequence that this has been will be obtained will be simply the product of the probability that m2 occurs here, m5 occurs here, and so on and so forth. Right, because of independent emission of sequences. So probability of a specific sequence S sub n is going to be p1 to the power np1, because m1 will occur somewhere along the line np1 times. Right, similarly into P2 to the power NP2 and P sub n small n to the power NP sub n. Do you all agree with this? Amitabh, some question there? Tarun?
Shouldn't it be equal to 1 by n? Because
1 by n? No.
n
If they are equally probable, if P1,
What I
P2.
mean is suppose n sequences are possible. So one equal probability has to be 1 by n, isn't it?
N sequences are possible. What does that mean?
Okay, what is case?
Right. One could take that approach and one will get to the same result. Right. This is easier to appreciate. Right. That is, your sequence consists of a number of independently emitted symbols. Right. Therefore, the probability of this specific sequence will be the product of these events, the product of probabilities of these events, which is what you are writing. This is the simplest thing to mathematically write. And the next important thing to appreciate is that this probability of a typical sequence that we have considered will be the same for all typical sequences, will be the same for all sequences for that matter, because all sequences have the same precise structure in terms of M1, M2, M sub n, right, provided n is sufficiently large. Right? So it's same for all typical SNs. What does it mean? That this sequence of this n long sequences, that message sequences that we have constructed, provided n is sufficiently long, sufficiently large, are all equiprobable. Okay, so this is the trick that I am playing. I have constructed from the original message source, which was not equiprobable, a new message source which is equiprobable, right? Where the new message source emits not a single symbol but a sequence of n symbols where n is very large. Okay, is it clear? And I have got an equiprobable source.
And any sequence, the number of times which the MI repeats is fixed.
Is fixed in terms of these probabilities, right? So I have got a new source which is equiprobable, right?
So is it fixed or it converges to a fixed value? Number of
It is
times
fixed.
any single
Well, if n is sufficiently large, it is fixed. np1 times will be a fixed number, right? As n tends to infinity, it will be some constant value.
That means you can still differentiate between two sequences.
Yes, of course. The sequences are all different, right? But they all have the same probability, and the probabilities are each equal to p this probability.
Most of the sequences are same.
No, the sequences have the same structure.
Same structure.
Structure in the sense that M1 occurs so many times, but where do they occur?
The permutation is not
The
together.
permutations are different. Where do the precise locations of M1? Where are the precise locations of M1? They will be different from sequence to sequence, right? But they all have the same number of occurrences of M1, same number of occurrences of M2, and so on and so forth. So the sequences are really different, but their properties are the same, and that is finally reflected in the fact that they all have the same probability of occurrence. Okay? Yes.
This is not going in the wrong manner. First we are finding out the number of times a particular symbol occurs from assuming the size to be infinite. Then we go back to the probability. I mean,
What is wrong with it? I don't understand
first
your.
we find the number from the entire sequence and then find the probability of entire sequence occurring.
Yeah, one could do that, and that will be a slightly more lengthy procedure. But what is wrong with this argument? I want. You said that there is something wrong here. I would like to understand what is wrong here. Because my argument is that you have a specific sequence, right, in which these various message symbols are emitted independently, each with a probability as given over here. Now, if I want to find out the probability of this specific sequence, well, I have to find out that M1 occurs here, and that occurs with a probability P1. It will also occur somewhere else with the same probability, somewhere else with the same probability, total of np1 times. What is the probability of these happening? p1 to the power np1, right?
Sir, if these are independent, then how can they form sequence?
Sorry?
If these are independent,
Yes.
then how can they form sequence?
Okay, I think maybe something is wrong in my presentation. Let's just quickly go through what we are doing. We have to start with a message source whose dictionary is these n message symbols. Now we are thinking of this message source emitting a sequence of symbols from its dictionary, one after another, and we are looking at n such emissions, right? That is, we are not trying to encode each emission as it is emitted, but we are letting them accumulate over a length of n symbols, and then we are thinking of coding them, right? That's the reason why I am doing that is because I want to construct an equiprobable message source out of this non-equiprobable message source. This new source that I have constructed, its dictionary is all possible sequences of length n of this kind, all possible sequences, right? What will be the value of such sequences? What will be the number of such sequences? N to the power n, small n to the power capital N, right?
Okay, but
Then, sir, if we are forming equiprobable, then probability of a particular sequence will be equal to 1 divided by n minus 1.
This is precisely it will turn out to be, right?
so we consider the case when the number of times each mi appears is fixed. So in this case, this won't be valid. This is called time when each.
नहीं यार, the number of times each mi is fixed. Each mi is S1 S2 अगर आया वो they are occurring the same number of times.
So in each s for any random guys, the number of times which m1 appears is fixed. Yes, sir. In that case, the probability cannot be n to the power of n.
Words consider कर लो ABCD मान लो
This is where
words of fixed length consider कर लो.
sir,
Yeah, let me just, maybe this statement is not correct then. Yeah, that statement will be true if each of these were already equiprobable. I think you are right. I shouldn't make that statement. Yeah.
what's sir?
That is, if each of these was equiprobable, then perhaps I could have made that statement.
Which statement?
That is, the total number of possible kinds of sequences you can have here is small n to the power capital N.
Capital N to the power capital N.
How can it be capital N to the power capital N?
Yeah, the n difference
Huh?
there only when.
Sir, what Manish was saying that
Because we cannot have an arbitrary number of m1 or m2 or m3 in this sequence.
Sir, what is this, sir? This n to the power, small n to the power capital N would be valid when each of the symbol is uncorrelated with the previous one.
That it is.
Sir, but we are even otherwise assuming that although they are uncorrelated, if we take a very large sample, the number of
We are not assuming that. That comes from the definition of probability. That comes from what the relative frequency implication of probability. This is not an assumption.
so if we assuming that
No, we are not assuming that. Okay? If we have n very large, Varun, please let there not be so many parallel discussions. If there is a confusion, let's try to resolve it here. If we have n trials, in each trial we have these are the options available to us with these probabilities. This is the experiment we are conducting.
so the point is this, so when we talk about probabilities, we talk about some correlation, don't we?
The correlation is zero. The correlation from one emission to the next emission is precisely zero. We are saying they are independent. Now this occurs with a probability P1. This also occurs independently of what has occurred here. This is the correlation you are referring to? Okay.
So, especially one thing leading to another. No,
No, it's okay, sir. It's okay. So only states are independent.
Sir,
2 and M5.
Sir, if these are independent and number of m1 and m2 are fixed, then there will be only one sequence.
So there will be more
so how do we arrive at this?
It's clear to me that your basic fundamentals in probability are not very clear.
Sir, how do we arrive at the value P1 P2 P?
Sir, let's leave it, sir. Let's proceed further.
Okay. Okay. Let us. I think we are going into circles. without really achieving anything. So we'll skip this discussion any further. In a nutshell, please think about it, and it's very easy to appreciate this fact if your basic fundamentals of probability are understood, that this fact comes from the definition of probability, assuming that these n pickings from this source are independent of each other. That's all. And once this structure is there, I think it is quite obvious that a specific sequence, a typical sequence, will have this probability, and this probability will be independent of what typical sequence you pick up. Right? These are the broad points to understand. Don't try to confuse yourself by looking into in a manner which really just unnecessarily confuses you. These are the essential facts. Facts are the emissions are independent with these probabilities. We are considering n emissions, independent emissions. Therefore, that leads to this structure of this frequency of occurrences of M1 to M sub n. Right? Because of that frequency of occurrence of individual M sub i's, a typical sequence will have this probability of occurrence. These are the broad facts.
Therefore, number of sequences will be equal to 1 by Psn.
The number of sequences will be equal to 1 by Psn. Quite right. Right? Because they are equiprobable. You're quite right. In fact, I'm going to use that fact now.
All are equally probable and exclusive.
Okay? All right. If you still have some doubts, let's discuss them separately later, because I've spent already too much time on this, much more than I had planned to. Now, how many bits, how many binary digits will I require to encode this equiprobable message source? This I know now, right? What is the value? What is the, let me denote this by L sub n as the number of binary digits required to encode this equiprobable source. It's equal to log to the base 2 of 1 by of this probability, right, which is P S n. Right? That basically comes from this interpretation that you are just mentioning, that we can have total of this many sequences of this length, right, or this structure, because we are specifying a structure. Okay. So let's try to simplify that. Substitute for P of Sn as this product of probabilities. What will I get? This is 1 by P1 to the power np1, 1 by P2 into to the power np2, and so on. So if I take the log of that, what will I get? Substitute from this expression into this, and use the properties of the logarithmic function, and that will give you n times pi log to the base 2 of 1 by pi, right? I going from 1 to n. Is it clear? But what is the summation? That by definition is entropy of the source. Okay. So what do I find? That to encode a sequence or a symbol coming from this new equiprobable source, which consists of n original symbols, right? This new equiprobable source emits n symbols at a time of the original source. You require so many binary digits on an average, right? Therefore, in terms of the original binary source, in terms of the original source, what is the average number, average length of the code? This divided by, because this represents n symbols of the original source, is equal to h, which proves what I wanted to show, that one can, even for non-equiprobable message sources, have a procedure by which I can represent on an average each symbol emission by so many binary digits. So many bits, because this is I'm writing in terms of length.
Could you please show the previous slide?
Sure. What is your question? L is the length required to encode an individual symbol of the original source, because this representation is representing n symbols, a sequence of n symbols. All right.
And it is equal for all the symbols. Is it?
What is equal for all the symbols? L, or this is an average value, so that average value of course is not an equal value, right? Average has a very specific meaning. I'm assuming that you all understand what is average. Yes.
Sir, from this argument, this is some sort of data compression. Is this?
This
Sir, are you encoding sequences into lesser number of bits? That's what you're doing.
it's not really. It's not like that. Yes, data compression is related to what I'm discussing, right? But that is secondary, because at the moment there is no concept of compression coming into the picture. At the moment I'm asking the question, if I have a particular source with a particular entropy, what is the minimum number of binary digits required to represent this source efficiently, right? And the answer is, it is related to the entropy of the source. So when you are doing a data compression, or when are you doing a data representation, you must bear this in mind, right? Your method of representing the source, how good it is, will be measured by this fact, right? Let me come to this point. In fact, I'm coming to elaborate on this point a little more. This is the average number of bits per symbol of the original source, right? Is it obvious? Average number of bits, let's say average length of the code per symbol.
So, a capital N was the length of the total computation, or if you would.
I had considered a group of n symbols which were being represented by so many final encoded sequence of this length, right? So per symbol basis, on an average, you require simply HM bits per of the original source. All right. Now it can be indeed shown. See, what I have shown so far is that the average code length required to encode this message is HM, the entropy of the source, per average over the symbols, over the set of symbols that you are working with, right? It can further be shown, I'm not going to do that, the proof of that is rather tricky, that in fact this is a minimum value that one can hope to get. This is what the argument that we have given is only for the average value, right? The minimum average value that we can hope to get is indeed the value of this entropy of the source, right? And that is precisely what the source coding theorem states. Let me just. It's not obvious, because what? How do we know that it is a minimum? You have to prove that there is no coding procedure that exists which will require finally a code length less than the entropy, right? You have to prove that. I have not proved any such thing. All I have proved is from intuitive reasoning that this is I can devise procedures by which I can achieve this average length, right? But maybe there is a coding procedure which exists which can take us below this, right? One has to explicitly prove or disprove that fact. That's precisely source coding theorem, what source coding theorem does for us, but we are not going to go into those elaborate mathematical proofs. So the source coding theorem states that to encode a source with entropy HM, we need on an average a minimum of HM bits per symbol or per message. Okay, and you can't do better than that. So in other words, we can expect your optimum source coder to produce an average word length equal to the entropy. Okay.
What makes this on an average?
On average, because your different symbols have different probabilities. Your different symbols therefore may be requiring different lengths for representation, right? But the average length is entropy, right?
So the average is
Average over the symbols.
Minimum average.
This is the minimum value of the average that you can
effectively
expect.
coming out because you're actually taking the average of the total number of sequences possible and dividing by the number of size.
You see, that average is implicit because I consider equiprobable sources. For equiprobable, the average is equal to the length of each symbol, right?
The average is
But-
taken not arithmetic average, it's probabilistic average.
It's a probabilistic average over the symbols because each symbol has a different probability, right? Is it clear? There also the average is being taken. When I wrote this expression, right, this was the average value. In fact, I should write here average. It so turns out that in the equiprobable case, the average and the actual length are the same, right? So everywhere we are really dealing with average values. Okay, what is the implication of this? The implication is that in order to efficiently utilize your channel or which you are doing your transmission, one of the first things you should think of is making sure that, you see, ultimately we are going to have limits on how fast I can put data on the channel, right? And how fast I need to put data on the channel will depend on the kind of source emissions I have, how fast the source is emitting data for transmission onto the channel, right? Now, if I can encode by source representation properly, if I make sure that the representation is as efficient as theoretically possible, then I'll be putting on the minimum possible demand on the channel in terms of data rate requirements, right? That is the basic significance of source coding. And in this sense, the kind of source coders that we discussed, we have already discussed some source coders for your information without you perhaps knowing that they are source coders. No, source coders are basically devices which essentially give you digital representation of your sources, and that is the very first thing we started discussing in this course, namely your PCM, your delta modulator, and your adaptive delta modulation, and those kinds of devices, right? These are all source coders. They are doing digital representation of your signals, right? Now you should go back and see whether those are efficient source coders or not. We already in fact discussed to some extent how to make them efficient. For example, we said for analog to digital conversion we could use companders to make them more efficient, right? Making use of the probabilistic structure of the values that you are going to get out of the source. But even with all those modifications, you will find that your conventional source coders for typical sources for which you will be using them will be very, very inefficient. For example, if you put that A to D converter to represent speech signals, you will find that you are ending up using an average code length out of the A to D converter which is much larger than the entropy of the speech source. Okay?
Are they being replaced?
Of course, that's a very major important thing for communication systems and communication theorists, right?
How are these implemented?
We can't answer everything in this question in this small little hour, but we'll certainly have occasion to discuss that. We have methods by which we can represent. You see, now therefore it depends on what kind of source you are representing. When you just put an A to D converter, we don't really try to see what is the kind of signal that is coming into the A to D converter. Now you have to start saying what is the kind of signal that is coming to the A to D converter. It is because what we are really trying to do now is represent efficiently that source, right, rather than just doing a straightforward crude A to analog to digital conversion. For example, if it is a speech source, we have to understand the nature of the speech signal, understand what is its entropy, and then from these two understandings devise methods by which to represent source, the speech source, by a rate as close to its entropy as possible, right. There are all kinds of techniques for doing that, and they are being used in practical systems. Okay. For example, for speech we have Foment vocoders, there are LPC vocoders, and there are all kinds of other source coders. Similarly for images, the kind of data compression techniques that are, these are called data compression techniques, right, because basically we are trying to compress data over what you would do by an A to D converter, straightforward A to D converter. Okay. So we'll come back to this if we have time. Now coming back to this discussion here, so we have a method by which we can achieve the efficient source coding for discrete sources. Do you think it's a good method or a bad method that we discussed just now? It's the best possible method, but yes, in terms of achieving efficiency, it is very good. But do we have some problems with this method? That is a question.
Providers know the sequence, the n bit.
No.
You need to know the probability.
So the n bit.
Probabilities you'll have to know, because after all, your source is being modeled as a probabilistic source, so it has to be known. There is no disadvantage in that. One can study the probabilistic structure of your source. No, a particular source, let's assume that a particular source has a structure. Now, is there anything wrong? Let's put it this way. Let me make that question more specific. Suppose I have a probabilistic source in which I have n message symbols, each emitted with those probabilities P1 to Pn.
The average size of the symbol is varying. Because
that also is not a disadvantage.
so how do you
In fact, we expect, like in Morse code, we use different symbols for different code lengths for different symbols. It's in fact required. If you want to achieve entropy, that will be required. You can't do anything about it.
So what actual doing transmission only
The real problem is you're not catching on to that. The value of n that we need
is very large.
in this procedure, right? What does it mean? The coding delay is infinite. I have to wait for the source to emit infinite number of symbols before I can start encoding it. It's not practical, number one. Number two, it may be very annoying in real life situations, right? You may not, for example, if you're trying to do an encoder for speech, and if your encoding itself requires you to wait for such a long time, the other guy will keep on waiting for your response after you have spoken, right? So it's not a practical way of doing things if n turns out to be very, very large. So therefore, we'd like to think of other coding procedures, source coding procedures, which don't have to wait for such a large time, but which will achieve practically the same thing in terms of efficiency, in terms of representation, efficiency of representation, right? Now, certainly we will not be able to do as well as we are able to do with this ideal procedure, right? The number of bits that we may end up using may be much more than the entropy of the source, the average number of bits that we may end up using. So the question is, what are these procedures? Now, there are a number of such procedures. These are called compact coding procedures. We will discuss one of them, which is very popular. It's called Huffman coding. Okay, are you familiar with Huffman coding? Okay, now you can find out what they are. And in fact, this can be shown to be an optimum procedure for memoryless sources. Okay, the basic idea is we like to encode not with n equal to infinity, but with n equal to 1. That is, as each symbol is emitted, we are directly encoding it, rather than waiting for n symbols to be emitted and then encoding it afterwards, right? And what does encoding mean? Encoding here means assigning to each symbol a specific digital representation, binary representation.
Probabilities a priori.
So otherwise,
Yes, yes, we'll have to know that. We'll have to know the probabilities. Even in that model, we had to know the probabilities, right? Because unless we know the source, unless we know the statistical properties of the source,
If
we cannot
large number of n symbols, then we can find out probability.
Yes, sir.
That's what I understand.
That is what
Then
was-
in that case, we can find out probabilities. We don't need to.
No, but that procedure is not about finding the probabilities. That procedure is given that the probabilities are unequal, how to produce a code.
So there was
Right?
where the confusion was lying. So he was thinking on that finding.
In this case, we can find out probabilities.
No.
If we collect n number of symbols, then
Probabilities you will have to find. You can study that. After all, you are going to look at your source very seriously. If you want to use these optimum procedures, you would have offline independently studied your source very thoroughly and have a model for that source, right? Once you have a model for that source, the question is how do I use that model efficiently? That is a question, limited question we are looking at. We are not looking at the first question of how to model that source.
we have modeled the source already.
Assume that we have modeled the source and we have this model available to us. Any other question?
So
Model the source, why do you have to wait for n?
Yes, sir. That thing that
We have to wait for n because of the fact we wanted to convert a non-equiprobable message source to an equiprobable message source so that we could get efficient coding. Oh, I think I probably made a mess of this lecture then. I don't know. You see, I do not know of any coding procedure based on, so far when I was discussing this, I had not told you any coding procedure by which one could actually hope to achieve a symbol representation for each of these symbols which requires on an average a length equal to hm, right? So I said I will tell you one procedure by which I could do so. How? By converting this non-equiprobable message source to an equiprobable message source in which I am consider a message sequence of length n, okay, for which I already know that this can be done. I repeated that many times, right? This is the point I was trying to emphasize at that time.
No, but that was just to calculate the.
That was to demonstrate that it is possible
to convert it into
to
probability.
to achieve this value of representation, that is average number of symbols, average binary digit per symbol equal to entropy. To get to that result, I went through that argument.
So could you repeat what you said?
The argument was that I want to represent this non-equiprobable source by an equiprobable source such that all the probabilities are same, right? For which the result is known to me, and I wanted to use that known result to evolve a coding procedure for this source. Okay? That is the objective of what we did earlier. I hope it is clear now. Okay? Alright, it doesn't matter. And now I am discussing another procedure which does not require you to wait up to infinity, right? Which requires you to, which can do the coding for you as each symbol is being emitted. But we cannot hope to get the same kind of performance as that procedure gives us. Performance in terms of representation vis-a-vis entropy, right? Average length being equal to entropy. We will expect the average length here to be more than the entropy, right? Let us see how much more it is with such coding procedures. Okay, and I'll illustrate this procedure as well as how good it is by taking a specific example. Okay, I think it's best to illustrate this coding procedure by an example. So I'll take an illustrative example, and that example is like this. I think I'll start with an independent sheet.
But sir, this will be optimum if there is equiprobable source already. And then this will
For
be
equiprobable sources, there is hardly any problem because any mapping is good enough. Okay. For equiprobable sources, we don't have to worry anything. We don't have to do anything special. Okay. Let's say I have a source. Just I'm taking this as a arbitrary example in which the source has 6 possible symbols. Dictionary of 6 symbols. Okay. And let's say these symbols are associated with corresponding probabilities which I am going to list, I am already listing them in the decreasing order of their probabilities. Let us say this has a probability of 0.3, this has a probability of 0.25, 0.15, 0.12, 0.10 and 0.08. Alright. I have a message source with 6 possible symbols with these corresponding probabilities. I have arranged these various symbols, message outputs, in the order of decreasing probability of occurrence. Okay. So this is my original source. This is the model for my source. Right. These are the messages which it emits, which it can emit in any unit interval with these probabilities. Right. Now, what I do is, the coding procedure proceeds like this. I construct a new equivalent source S1 with only 5 messages by doing the following: by clubbing 2 of the lowest most messages into a single message, single equivalent message. So I am constructing a new message source in which the dictionary is comprised of these 4, and the 5th one is the union of these 2 messages, that is either M5 or M6. I am counting that as a single message, right? Alright, and then I look at this 5 message source and again put the probabilities in their decreasing order. This new message, since they are independently emitted, what is the probability of this new message value? 0.18, because the union of these 2 events and each of them is independent, or not really independent, I should use mutually exclusive. Right. So this will be 0.30, then 0.25, and here we will write 0.18, 0.15 and 0.12. So these 2 together have been clubbed into a single message, and that message has appeared here in this. And I repeat this procedure. Again I take the lowest 2 symbols, club them into a single symbol, and construct a new message source which will become 0.27, so it will come here. .25, 0.18. Is that right? Fine. And I keep on doing this. Now I will get 0.43, which will be the largest, then 0.27 and then 0.25, correct? Oh, 0.3, 0.27. Fine. And this is where I stop. I stop when I am left with only 2 possible emissions, right? What do you think I have hoped to, what did I hope to achieve by doing this? Basically the objective was to finally obtain a source of only 2 messages with as equal probabilities as possible. Okay, that was the basic idea, and this procedure helps me to achieve that objective. Okay, and if these are as equal as possible, it will be reasonable now to do a coding procedure as if you are dealing with equiprobable sources, right? That is, I assign arbitrarily a code 0 to this and a code 1 to this, or other way around, it does not really matter, right? And now I proceed backwards. I trace the path backwards. I have to now distinguish between the 2 messages that comprise this message. This message is actually comprised of the union of these 2 messages, which eventually I have to distinguish between, right? So I represent this with a 0 0 and this with a 0 1, and this of course remains 1 because I don't have to do any distinction here. But when I go one step backward, I have to now distinguish between these two symbols. So I write here a 1 0 and a 1 1, and this becomes 0 0, and this is 0 1. Okay, keep on doing that. This will be 0 0, this will be 1 0, right, 0.25, 0.18 is 1 1, and this has got to be again distinguished between these two symbols. So I write here 0 1 0 and 0 1 1. Okay. Fine. Go to the last step. You get 0 0 here, 1 0 here. This was 0 1 0. This was 0 1 1, and this will become 1 1 0 and 1 1 1, and this is your final mapping by Huffman coding. M1 will be represented by a sequence, a binary representation of 0 0, M2 with 1 0, M3 with 0 1 0, M4 with 0 1 1, and so on. Right?
This is where that problem was, like in a sequence, let's say sequence of n symbols, how will we decide that it's
The size of
2-bit
or a 3-bit symbol.
coded word or a
No, but there we are not doing encoding on a single symbol basis. We are encoding on an n symbol basis. We have to distinguish between one sequence of n symbols and another sequence of n symbols and other sequences of n symbols. So each unique sequence of n symbols will have a unique representation, binary representation. That's all. So I will know the specific sequence that is represented by it.
Then how do we know that 0 1 0 is a 0 followed by 1 0?
Okay, that's a separate question, but has this question been answered? Tarun, have you understood what I'm saying, trying to say? In that procedure, I'm mapping this whole sequence by a corresponding binary sequence, and I have to decode also in the same way. I have to wait for the whole sequence to be received and then decode the whole sequence. It cannot be decoded on a symbol by symbol basis. One has to wait for the infinite sequence to be encoded, this infinite sequence to be transmitted, received, and then you have to decode that as a whole sequence together, not on a symbol by symbol basis. But in this case, I can do on a symbol by symbol basis. I can look at 2 bits and say that this is M1, or say that this is M5.
Sir, that's not my question. How do you decide whether to look at 2 bits or 3 bits?
Oh, was that your question?
Yes, sir.
I thought you were referring to the previous procedure.
No, sir, here, like when we
Okay, then yours and Varun's questions are the same.
I'm saying that if it is
Okay.
0 1 0, how do we know 0
Okay.
followed by 1 0?
Fine. That question has a different answer. The answer to that question is, it can be shown that the Huffman coding procedure is what is called a comma-free code. Right? That is, one doesn't require a marker between code symbols. See, to do that, one way would be to send a marker in between that, right? Some specific symbol which says that, okay, one code word is over and the next code word is starting. But that will be inefficient because you are again using up marker space, right? It can be shown that given a particular received sequence, if there is no error, right, the Huffman code can be uniquely decoded. Okay, there is no other way of allocating sequence of bits to the original message sequence other than a unique way, right? That is okay. I think the best thing is to construct a simple example and see that you cannot indeed cause any other allocation except the right allocation, right? I would like you to do that as an exercise. It's a very simple exercise. Okay. In any case, our time is up now. But before I finish, let me make a simple comment on the efficiency of this code, how good this coding procedure is. For this specific situation, Suppose I was to compare it with entropy. Entropy you can calculate easily. You're given the probabilities. It will be, if you do that, I'll just give you the value. You can verify it. I think it's 2.418 or something bits per symbol. This is the entropy corresponding to these probabilities. You can also compute the average length. How? This will be 2 into 0.3, 2 into plus 2 into 0.25, plus 3 into 0.15, plus 3 into 0.12, plus 3 into 0.1, plus 3 into 0.08. This is the average length for the final code that you have achieved. And that turns out to be 2.45. Right? Obviously it has to be greater. But it's very close. Right? In fact, one can define what is called code efficiency as HM by average length. And that's very, very good. That's nearly 0.976 or something. I'll start from this point next time. Right? I hope to do this plus much more, but thanks to our confusion in between, we couldn't do that.